Okay, today we are going to talk about the superchargings and turbochargings. These are the methods that we use to increase the engine powers and the engine efficiencies. Right? We do increase the power and efficiency of the engines by using the air compression device, which is the air compressors, right? But in here, we will call it superchargers or turbocharger, right? So we need a compression device in order to compress the air, okay? And that device we call is a superchargers or the turbochargers, right? So by doing this, right, it means we can add more fuels into the cylinders because of the amount of air that we introduce into the engines. Now it have an increase in pressures, right? The pressure of the air can be increased from 20 kPa to 250 kPa. Right, this is the length of the pressure increase in the air, right, due to the superchargers or the turbochargers. And the density of the air that we introduce also increase. So we can add more fuels. And that's the reason why the power of the engines and also the efficiency of the engine increase, right, due to these more fuels that can be introduced into the cylinders. Right? But there's a limit on introducing this air, right, due to the pressure increase because of the knock limit for the SI engines. Right? In the SI engines, right, if the pressure of the air increase too much, right, during compressions, right, knock may happen. Right? Knock is mean pre-ignition before the spark happen. Right? So in that case, right, when we introduce the amount of the air through the supercharger or the turbochargers, right, we have to limit the pressures that we can increase in the air, right, because of the knock limit in the SI engine. But for the CI engines, right, for the diesel one, there is no knock limit on this because it, in the CI engine, we have no spark plugs, right? The ignitions happen because of the compressions, right? It's different from the SI engines, right? So using turbochargers or superchargers in the CI engines, right? There is no limit on this. So they both are used extensively on the wide range of the diesel engines. Okay. This picture gives you the 6 basic ways of doing the superchargings and the turbochargings. We have 6 basic ways that we can equip the superchargers or the turbocharger configurations into our engine in order to increase the pressure of the air that we are going to introduce into the engines. The first one we call is mechanical supercharging. The mechanical supercharging, right, in which we have a compression device, a compressor right here, that is driven by the engines directly, right? It's driven by the engine here. So it receives the power from the engine. So this is considered to be a parasitic load to the engines, right? Because it receives the power from the engine. So it will compress the air and send the high pressure air into the engines for combustion. Okay, so this is the first configurations we call is a mechanical supercharging. The second configuration we call is a turbocharging, right? In which now our turbochargers here. Oh, by the way, the first one they normally call superchargers, right? The second one they call is the turbocharger, because now our compressor receive the work from the turbine, where the turbine can deliver the work to the compressor because of the exhaust that come out from the engine. The exhaust that flow out from the engine, right, before it leaving to the atmospheric, to outside air, to the atmospheric conditions, right, it will flow through the turbine in order to drive the turbine, right? And then the turbine will deliver the power to the compressor here, right? So the air flow into the compressor will be compressed and sent to the engines, right? This is the second configuration called the turbochargers. The third configuration is called the engine-driven compressor and turbocharger, right? In this configuration, we have two compressors, right? The one here is the low pressure compressor driven by the engine, okay? But since it's a low pressure compressor, right, the amount of work delivered from the engine to drive this compressor is low, right? The second compressor is a high pressure compressor, right, which receive the works from the turbine, right, where the turbine can deliver the work to the compressor because of the exhaust flow from the engine here. Okay, so the engine-driven compressor and turbocharger is consists of one compressor driven by the engines, another compressor which is a high pressure driven by the turbine. Okay. The fourth configuration is called the two-state turbocharging, right, where we have two turbocharger work together, right. The top one, right, the top turbocharger, right, is the low pressure one, because we have a low pressure compressor here, right, driven by the low pressure turbine, and we have high pressure compressor driven by high pressure turbine, right. So the air is compressed twice, right, and in the same time the exhaust will be expanded twice, first in the high pressure turbine and second in the low pressure turbine. Okay. The fifth configuration is called turbocharging with turbo compounding, right, in which we have only one compressor here, which is driven by the high pressure turbine here, right? And this high pressure turbine again receive the exhaust from the engines, right, in order to drive this high pressure turbine and deliver the work to the compressors. Okay, but for these configurations, we also have another low pressure turbine that receive the exhaust flow that flow out from the high pressure turbine, right? It still have more power, so we let it flow into our low pressure turbine here, right? So using this, the amount of work that come out from the engine now, right, can be in two parts. The first part is from the engine itself, and the second part is from this low pressure turbine. So this will combine together, right, to deliver the power out from the engines. Right? So in this case, we use the exhaust not only to drive the high pressure turbine in order to deliver work to the compressors, but this exhaust that come out can also deliver the work for us to use, right? So it will incorporate with the work from the engine all together, right, through this low pressure turbine here. Okay. The last configuration is the turbocharger with intercooler, where we add one more device, which is called an intercooler here, in order what? In order to reduce the temperature of the air before introducing or inducting into the engines. Right? The reason is because we want to have a high volumetric efficiency, right? Because if we can reduce the temperature of the air that flow into the engine, it means the density of the air reduce. The density of the air reduce, it means the volume of the air reduce, right? So we can have more space or higher space, right, to introduce more amount of the air into our engines. Right? So all these are 6 basic ways to do the superchargings and the turbochargings. Okay, this picture show you the mechanical supercharger with intercooler. The intercooler is right here, right? And our supercharger is here, right? We call it a supercharger because you can see that the engine deliver the work to our compressor. Right? So the compressor here, which is driven by the engine, can draw the air, compress the air, and send the high temperature air into the intercooler. This intercooler will reduce the temperature of the air before sending it into the engines. Right? So in overall, we will have the higher volumetric efficiency. And if we can have higher volumetric efficiency, the power of the engine increase, the efficiency of the engine increase. Okay, this is the actual pictures, right? When you install the superchargers into your engine. This is the compressor, this is the air filter. Okay, so the compressor will be driven directly from the engines to compress the air and send this compressed air into the engine. Okay, this is show you the turbochargers, right? Where we have a turbine here and a compressor here, right? The exhaust represented by the less arrow, right, will fall into the turbine and dry the turbine before it leaving out to the atmospheric conditions. Right? The air will flow into the compressor because the compressor is run by this turbine here, right? So the air will be compressed and then distributed to its cylinders. Okay, this is show you the actual pictures of the twin turbochargers or a two-stage turbocharger because we have two turbocharger here, right? The first set is right here, right? And the second set is down here, right? This is the compressor. You can see the skin color is different, right? And this is the turbine, right? Where the skin color is dark. Okay, so you can see two sets of the turbocharger that is installed into your engine room. Okay, let's first talk on the superchargers. As we already know, it is a mechanical driven directly off the engine crankshaft, right? So the power to drive the supercharger is considered to be a parasitic load on the engine output, right? Because some of the engine output, right, instead of deliver for us to use, some of this power have to give to the supercharger in order to run the supercharger. So this is one of the major disadvantages compared to the turbochargers where we use the energy from the exhaust gas. Right? Other disadvantages that come out from the supercharger includes the higher cost, the greater weight, and also the noise. Right? Because you have to install one more device into your engines, right? And now your chassis, your engine chassis have to receive more weight on the engine because of the superchargers. And when it operates, it creates the noise in your engines. Okay. But the good part about having the superchargers, right? We already talked about the bad part, right? In terms of the loading, in terms of the cross, in terms of the weight and noise. But the good part of having supercharger is that it is in a very quick response to the throttle change. Right? So this device can provide a quick response to the loading that happened to the engines. Now, when we talk about the throttle change, it's always referred to the loading that happened to the engines. Right? So this supercharger give you a quick response or a fast response because of it has directly a mechanically linked to the crankshaft, right? Because it directly connects to the crankshaft of the engine. So whatever happened to the engines, this supercharger also feel it. And by feeling whatever happened to the engine, it can give a quick response to whatever engine needed. Okay, so any engine speed that changes in terms of quick response, it means it will be immediately transferred to the compressor or to the superchargers. Okay. The two pictures below here show you the flow process that happen in the compressors. Right? I show you here both on the TS diagram or the temperatures and the entropy, right, on this left hand side. On the right hand side, you see the pressures and the specific volume. Okay. The letter S here stand for the ideal process, which is what? The reversible adiabatic compressions or the isentropic compressions. Right? A stand for the actual compressions. Right? So if you look at the TS diagram here, right, this device operates between two pressure lines. The first one is called the ambient pressures because it draws the air from the ambient. And then the second one we call is a cylinder inlet pressure because this is the pressure of the air after being compressed, that will flow into the cylinder. So it's that cylinder inlet pressure here. Right? In terms of isentropic process, right, we know that the entropy does not change. Right? So well, when we have the isentropic process, right, the line of the process is always in the vertical directions, right, to represent there is no change in entropy. Right? So the first one is always the actual one, right, because we draw the air from the ambient. Right? The second one can be either ideal process or the actual process here. Right? For the ideal process, we need to draw a vertical line here because there is no entropy change. But for the actual process, the question is, this line have to go right or go left, right? According to the principle of the increase of entropy that we learned in thermodynamics. Right? Everybody know that if the process have to happen, right, or actually happen, right, it always happen in the directions of increasing the entropy, right? So if we understand this, that the entropy have to be increased for the process to exist, right? So the actual process that happen in the supercharger will always go in the directions of increasing entropy. And that's why the actual process is always on the left hand side here, right? From 1 to 2A, actual one. Okay, for 1 to 2S, this is the ideal one. Okay, how about on the pressure and the specific volume diagram? Right, we also have two lines of pressure, right? The ambient pressure and the cylinder inlet pressures, right? The point one is the actual, right? Because we draw the air from the ambient, right? And in terms of isentropic process, right, we draw in the directions of decreasing of the specific volume. Right. the same as when we draw the actual process, right, in the directions of decreasing the specific volume due to compressions, right? It's common sense. When you compress, right, the air is denser, right? So the specific volume of the air will reduce, right? But the reductions of the specific volume is different because in terms of the ideal process, we will have higher reductions on the specific volume. That means what? That means we have higher amount of the air than the actual process here, right? So the isentropic process is usually, right, go into the far left further than the actual one when you draw on the pressure and the specific volume dry again here. Okay. Okay, that is the turbochargers. How about the that is the superchargers. How about the turbochargers? Right. For the turbocharger, the compressor is now powered by the turbine. Right. That this compressor is mounted in the exhaust. Oh no, a turbine, right? A turbine that is mounted in the exhaust flow of the engine, not the compressor. Right? The compressor is powered by a turbine, and the turbine is installed in the exhaust flow of the engines. Right? So we don't need to deliver any engine shaft output to this device. Right? And the only energy that used to drive this turbocharger is the wave energy in the exhaust flow, right? So we use the energy in the exhaust that we consider to be a waste energy, right, in order to drive the turbochargers, right? But even though we do not use the engine shaft power output to run this turbocharger, but the engine power output is still slightly reduced. It is still slightly reduced because we did put some device, right, to obstruct the flow, the exhaust flow, right. Instead that the exhaust flow can flow out easily from the engine to the ambient, right. It now have to flow to the turbine before it can flow out to the ambient, right, or to the outside, right. So doing this, right, will result in slightly reductions of the engine power output because the exhaust flow now cannot flow out smoothly, right, because of the turbine that installed in the flow part. Okay. Okay. So another thing is that normally we did normally we do want the engine to expand as much as possible, right? So the pressure of the exhaust that flow out from the engine is normally just a little bit above the atmospheric pressures, right? Because if the expansion stroke in the engine is too high, right? So that the exhaust pressure have the pressure lower than the atmospheric pressure, it cannot flow out. Right? So usually we will expand until the pressure in the exhaust just a little bit above the atmospheric pressures. Right? So that means when we let this exhaust to flow through the turbine, right, there will be only a small expansions, right, due to this small amount of the pressures in the exhaust flow, right. So there is only a small expansions that can occur through the turbine, right. So that means what? That means our turbine has to run at a very, very high speed, And when we talk about that high speed, look at the number, 100,000 or 130,000 RPM. Consider with the engine speed, which is about what, 3,000, 2,000 something, right? RPM, right? It's much, much higher because of a small expansion that can occur in the turbine, right? They need to run at this high speed because they want to produce enough power to run the compressors. Right? Without higher speed here, there will be no enough power to run the compressors. Right? So this high speed that happen along with the hot exhaust gas and also the corrosive environment, because the exhaust gas is not a clean gas, right? It's the product of combustions, right? So it can create the corrosive environment, right, in the turbine, right? So all of this high speed, hot gas, hot exhaust gas, and corrosive environment, all of this can affect the turbine, right? So to make a turbine, right, we need to consider a special materials, right, in order that this material, right, can withstand this hard environment, right? And another thing is we have to think also a long-term reliability, right, of this turbine, because when we produce it and use it, we want to use it for a long time, right? So both special materials and concern for long-term reliability, these two are the demand for making a turbine here. Okay. Another disadvantage of using the turbochargers, apart from special material, right, that we have to consider, right, it is called the turbo lag. Right? This is another disadvantage of the turbochargers, right? That is called the turbo lag here. What is the turbo lag? Turbo lag is a slow response to the change of the engine speed or acceleration, or in other words, the response to the change in loading of the engines, right, due to the throttle change, right? The throttle change means the loading change. When the loading of the engine change, the speed of the engine change, the acceleration of the engine change, right? So the turbocharger, right, have a characteristic of giving a low, slow response to all of these changes, right? And the response here we call is the turbo lag here, the turbo lag here, right? And however, right, this slow response problem of the turbocharger can be reduced by using a lightweight ceramic rotor. Right? So we consider the material that used for the turbine, it have to be a lightweight one, right? And apart from lightweight one, in order to give a high or a fast response due to the loading change of the engines, right? The material they use have to withstand the high temperatures also, right? So ceramics is considered to be a good material that can withstand a high temperatures, right? And then when it have a lightweight, it means what? It means it will have a little mass inertia, right? A little mass inertia, right? The mass inertia will affect what? It's gonna affect the rotations of the turbine, right? If the turbine have low mass inertia, the turbine can run faster, right, and respond faster. Okay, so this is one way, right? Consider about the special material, right, to make the turbine, and then material have to be able to withstand the high temperatures and also have a lightweight, right, in order to give a fast response to the change of the engine. Okay. Another way is by using a smaller intake manifold. a smaller intake manifold, right? So that the turbine can respond faster, right? Use a smaller one for the intake manifold. Here. Look at here, these two pictures give you the process that happened in the turbine, right? Give you the process that happened in the turbine. The less color again represent the ideal one, which is the isentropic process, right? The turbine also working between two pressures, right? The first one is the exhaust pressure that is on the top. The second one we call is a tailpipe pressure, not atmospheric pressure, right? Because the tailpipe pressure have to be a little above the atmospheric pressures, right? So the turbine will not expand the exhaust until it reaches the atmospheric pressure, right? It will expand the exhaust until it reaches some certain pressure that we call is a tailpipe pressure here, right? In terms of isentropic, again, we have zero change in entropy, right? So the line is become vertical, and again, for the process to happen, the entropy have to increase. So the actual process will go to the right directions, right? So from 1 to 2A here is the actual process. Same as when we look at the pressure and the specific volume, right? Due to expansions, right? The isentropic process will give you a smaller specific volume due to expansion than the actual process one, right? The actual process one will give you a higher amount of the specific volume. Yeah. Okay. If we go back to what we already mentioned, that the turbochargers use the energy available in the engine exhaust in order to run the turbine, right? And then the turbine go and run the compressors, right? But we all know that in order to use the turbine, right, for more efficient conditions, if we want to use the turbine in a more efficient conditions or higher efficiency in turbine, right? We have to use the turbine under the steady flow conditions. This is the condition that is most favorable for the turbine, right? Under steady flow conditions. But for our engines, which is a reciprocating one, right? We know that, right, it is considered to be an unsteady power setting device, right? That means the steady flow will never happen for the reciprocating engine because the flow will happen every time that the cycle finishes. So we have on and off of the cycle all the time, right? So the exhaust that fall out is not considered to be a steady flow. It is the unsteady power setting flow, right? So, but we still want to use the exhaust flow to run the turbine, right? So you can see a contradiction between these two. The turbine requires a steady flow in order for this turbine to be more efficient, right? But the exhaust, which is the energy that we use to run the turbine, the exhaust flow is an unsteady power setting flow, right? So that means in order to cope with this, our turbine to be able to work under these flow conditions, right? The turbine have to be designed properly, right? In order for this turbine to be able to accept this unsteady flow condition in its operations. and still work well, right? And still work well, right? To do this, we have two approaches, right? To recover the available exhaust energy for our turbocharging engines. The first approach we call is the constant pressure turbocharging. The constant pressure turbocharging. What does it mean? It means that we would like to have a constant pressure to happen, right? Not a pulsating pressure due to the pulsating flow that come out from the exhaust, right? So to do this, the exhaust manifold, right, the exhaust manifold have to be designed such that the exhaust pressure pulse will die out, right? The exhaust pressure pulse have to be die out so that the steady flow will happen when it reaches the turbine, right? What does it mean? It means the unsteady flow can be happen anywhere along the exhaust manifold, but before it reaches the turbine, it have to be a steady flow, right? In order for this exhaust flow to be a steady flow in front of the turbine, right, the exhaust pressure pulse have to be dialed out. Right? So how we gonna kill the exhaust pressure pulse? Right? To do this, the volume of the exhaust manifold have to be large. Right? So the sizing of the exhaust manifold, right, have to be big in order to accommodate the constant turbocharging. Right? So you have a steady flow because the steady flow come out with the constant pressures. Right? So the exhaust manifold have to be big or have to be large. Right? So the small pressure drop will happen in the manifold, right? And the constant pressure of the flow will be received before it reach the turbine here. Right? So in this picture, you can see that all of the cylinder will send its exhaust to this large exhaust manifold, right? And the exhaust will not come out at the same time for all cylinders, right? It will come out uh, from one to one or one by one, one by one, one by one, right? So whatever exhaust flow out here, right, it can be unsteady flow along the way in the exhaust manifold here until before it flow into the turbine, which is here, right? The constant pressure of that flow have to be reached in order to make sure that the flow that flow into the turbine become a steady flow, right? So the unsteady flow can happen in here, but when it flow into these regions, right, the steady flow must happen because the turbine work well under steady flow conditions. Okay, so this is one approach, right? In order for the turbine to receive the steady flow, right? Okay. Okay. Even though we do this by using this approach, our turbine can have a steady flow, but the disadvantage of this constant pressure turbocharging is what? Is if we let the pressure pulse to dry out, right, in order to have the steady flow, right, we also losing the energy that happen in the high velocity fluid, right? The energy in the high velocity fluid, right, will also dry out also, right? Because in order to have a constant pressure, the velocity will have to decrease significantly. Right? That means we have to let the velocity pressure to dry out. Right? So we will have only the static pressures of the flow. Okay. The second approach is called pulse turbocharging. Pulse turbocharging. Right? In pulse turbocharging, right, the turbine is run by using the kinetic energies. Right? So the turbine is designed to use the kinetic energy. So in this way, there will be no reductions of the exhaust velocity, right? And this kinetic energy, since it uses the kinetic energy, right? So in common sense, we cannot reduce the exhaust velocity. Otherwise, we're gonna reduce the kinetic energy also, right? So this kinetic energy come with what? Right? This kinetic energy is associated with the blowdown of the exhaust manifold. So it is the kinetic energy of the exhaust, right, that form the exhaust manifold here. Okay. So to maintain these kinetic energies, because we don't want to lose this kinetic energy or the exhaust energies, right, we have to use a small cross-sectional pipe, not like the first one that we use a large manifold, right? So when the exhaust flow from the cylinder into the large manifold, the kinetic energy obviously reduced, right? Because it flow into a larger sections. But for this case, we want to keep the kinetic energy or the exhaust velocity, right? So we intend to use a small cross-sectional pipe, right? So when the exhaust come out from the cylinders, right, we tend to keep the same diameter of the pipe along the way that the exhaust flow to the turbine. This is the way to keep the kinetic energy of the exhaust. Okay, so in here, right, we will use many pipe, right, because we cannot use just one pipe, right, because the reason is the amount of the exhaust flow, right? Sometimes it from one cylinder and then another cylinder, it may overlap with each others, right? So if 4 cylinder as shown here using the same pipe and our pipe is small, right? The pipe cannot accommodate the exhaust flow that come in sequence, right, from each cylinders, right? So in here, instead of using one pipe for all cylinders, we use one pipe for 2 cylinders, right? We use one pipe for 2 cylinder here, right? So for this 8 cylinder here, we will have 4 pipe all together that flow into the turbine, here, right? So when the first exhaust come out from these cylinders, right, it will flow in the small pipe throughout, right, before flow into the turbine here, right? So the kinetic energy is kept constant, right? The second exhaust that flow out from another cylinder, right, is kept far away from the first cylinder, right? So this two flow of the exhaust will not overlap. The flow will not overlap with each other because we have a longer distance, right, between these 2 cylinders, right? Same as the other cylinder here, right? The distance here is to prevent the exhaust flow, right, to be overlapped with each others, right? Because we use a small pipe, right? The reason because we use a small pipe, right? Down here is the same, right? And that the reason why we have to use more pipe in this case, right? Instead of having just only one common pipe in here, one common pipe in here. Right? So the kinetic energy of the exhaust will be kept constant before flowing into the turbine here. Okay. And again, right, the concept based on constant kinetic energy. But the problem that receive when we try to keep the kinetic energy is that we will have the problem on the unsteady flow. Right? The turbine will not receive a steady flow. Right? The turbine will not receive. Right? You look at these pictures, right? The flow is still a pulsating flow. Right? So this method, right, we call it a pulse turbocharging. That means we have to accept that the turbine will not receive a steady flow here. Right? It will receive a pulsating flow. Right? That means the efficiency of the turbine will decrease. Right? So to compensate for this deficiency, right, in order to reduce the effects of this unsteady flow that happen to the turbine, the pipe that we connect to the turbine will be grouped together. Right? The concept of grouping the pipe together is that we will group the pipe such that the exhaust pulse that happen, right, will be sequential and will have a minimum overlap. Right? This is what we try to do, right, for the sake of constant kinetic energies. Right? To keep the kinetic energy constant, right? The bad part is our turbine will receive the pulsating flow. So we will try to reduce this deficiency due to this unsteady flow or the pulsating flow to the turbine by grouping the pipe all together under the concept that the exhaust pulse will be sequential and the exhaust flow will have a minimum overlap, okay, in order to keep it in sequence here. Okay, so the first concept to keep the flow in sequence is shown on these pictures. Right? It's a two inlet pipe pulse converter system. Right? So the flow, the exhaust flow will be in sequence. Right? Under this concept, right, we will have two inlet pipe for the turbine. Two inlet pipe for the turbine here. Right? And we still have four pipe here. Four pipe here. Same as we mentioned before here. Right? We have four pipe here, but we have all four pipe to the turbine here. But in here we have only two inlet pipe to the turbine, right? But still have four pipe here. Right? The sequence happen what like this. Okay, if the exhaust come out from the green cylinder here, right? It will fall to the first inlet pipe here to the turbine. Right? The second flow to the turbine will now go into the second inlet pipe here, right? Which is what? The next exhaust flow will come out from the blue cylinder here, right? And then the third one now come back to the first inlet pipe. That means the yellow cylinder now will deliver the exhaust, right, through the first inlet pipe, right? And then the next one now, right, instead of this blue cylinder, now it's going to be a red cylinder that will fall into the turbine through the second inlet pipe, right? So this is the sequence on how each exhaust flow from each cylinder will flow into the turbine by using two inlet pipe. It's alternatively flow between the first and the second inlet pipe to the turbine. Okay, this is what we call sequential two inlet pipe pulse converter system. Okay, how about the concept of minimum overlap? Now, for the minimum overlap here, we will use one inlet pipe to the turbine here, the one inlet pipe here to the turbine here, right? So each cylinder here will have different stroke, right? For example, I show you here, right? The yellow one have the intake stroke, the green one has the compression stroke, the red one has the combustion stroke here, or the power stroke here. The blue one have the expansion stroke, right? And then the blue, another blue here, right, have the intake, and then compress for the red, and power stroke for the green, and yellow stroke for the yellow one for the expansion stroke. Okay, so the stroke in each cycle, right, if it go like this, then okay, you see that the first exhaust come out from what? From the blue one here, right? So the first exhaust come out from the blue cylinder will flow into the turbine here, right? The next exhaust will come out from what? From the first one, right? Come out from this, from the left. Let's see, okay. The first one come out from the blue color here, correct? Okay, the blue color here. Okay, the next exhaust come out from where? Okay, so the yellow then become compressed, right? The green one become powers, right? The red one now become expand, right? And then the blue one here become the blue one here become, let me see, okay, okay, let me go back over again. Okay, just a little bit confused. Okay, the yellow one is intake. Okay, let's go over again. The yellow one is intake, the second one is compressed, the third one is combustion or power, and the fourth one is the expansion, right? Okay, so the first exhaust come out from the blue. Okay, and then the second exhaust come out from another blue here, because the green one become intake, the red one now become compressed, and the blue one become power, and another blue, this blue become expand, right? And the next one will be the less color, the less one, right? And green one and the yellow one, right? So the exhaust will fall like this, and this will give you a minimum overlap here, right? Because the exhaust will fall, right, from one, and then from another one like this, right? And then the last one, the green one, and the yellow one, right? So this is what happened, right, if you use the concept of the minimum overlap, right? Because you use one inlet pipe, right? So the exhaust will flow, right, in sequence here with minimum overlap that can occur, right? Minimum overlap is mean there is some overlap, but the overlap is so small, right? And this overlap will not affect the performance of the turbine that shown in here. Okay. Okay, so that is the way that we try to use the turbine in a more efficient way, because we know that the flow that flow into the turbine is not a steady flow, right? It is a pulsating flow or the unsteady flow, right? So in order to reduce the effects of that kind of flow to the turbine performance, right, we can use either the constant pressure turbocharging or the pulse turbocharging. The constant pressure means we will try to die out the pulsating flow, right? But for the pulse turbocharging, right, we try to keep the kinetic energy, because if we dry out the pulsating motions, we also die out the kinetic energies, right? So the amount of the energy that flow into the turbine will be less, right? So the second approach that we use, the pulse turbocharging, is we try to keep the kinetic energy is the same, and that means our turbine, right, will experience the pulsating flow. So what we try to do is we try to minimize the pulsating flow that will happen to the turbine by either let the flow run in sequentials, right, run in sequence, right, in order that it will not the overlap. Right? Run in sequence means there is no overlap. Right? Another way is to minimize the overlap that happen. Right? We allow the flow, the exhaust flow, to be overlap, but little overlap will happen. Okay, so there are two concepts. One, the first one, there is no overlap as long as the exhaust flow run in sequence. Run in sequence. We can do this by using two inlet by here, right? So we let the distance, right, to keep the sequence, the distance of the pipe, right, to keep the sequence of the exhaust flow to happen, right? In the minimum overlap, we have only one inlet pipe. We have only one inlet pipe, right? Because we do allow the overlap to happen, but just want the overlap to be minimum. That is okay. Okay. The next one will be the type of the compressor use. Okay. Type of the compressor use. Okay. There are two types of the compressor. Right. The first one is called the positive displacement type, and the second one we call is a dynamic type. Dynamic type. Okay. For the positive displacement type compressors, right, the way they do is the volume of the gas is trapped, right, inside the compressors, and it is compressed by the movement of the compressor boundary element. Right? The compressor boundary element is what? It depends on the type, the compressor type. Right? For example, if you use the type of the positive displacement compressor with our what? The loose bore here, right? Then the compressor boundary element is the truth of the bore here, right? The truth of the bore, right? In here we have three tooth together, right? For the root of the bore here, right? Or for the vein here, right? The compressor boundary element is the vein, right? So the gas volume is trapped inside and compressed by this element. Okay, for the screw, right, this is the boundary element, right, of the compressor. Right, is the compressor boundary element here, the screw here. Okay, so the positive displacement type compressor is normally used in the superchargers, right? So the supercharger is normally used the positive displacement type compressor, right? And it runs at the speed about the same as the engine speed, because it, it receives the power delivered from the engines. Okay, and it receives directly. So the speed of the engine will determine the speed of the superchargers. Okay. The second type of compressor is called the dynamic compressor. The dynamic compressor. The dynamic compressor will use a rotating element, not the boundary element. like this one. Right? It will use the rotating element, so the element have to be rotated. Right? And due to the rotating motions, right, it will add the tangential velocity to the flow. Right? And this tangential velocity will convert into pressure in a diffuser. So by this, it means what? The pressure is built up in two states. The first one, the pressure is built up within the rotating element itself because it's rotated. Right? And due to this rotating element, it will create the tangential velocity to the flow. Right? So the flow have the tangential velocity. So when the flow leaves this rotating element into the diffuser, right, this tangential velocity or the kinetic energy along with this tangential velocity will convert, right, from kinetic energy into the pressure energy, and this happen in the diffuser. Right? So first, the pressure is built up by the rotating element. Second, the pressure is built up in the diffuser where there is no rotating element, but the pressure can build up because of the kinetic energy conversions. Okay, so there are two types of the dynamic compressors and also the turbine. Right? The first one is called a radiant or the centrifugal type. Right? And the second one is called the axial flow. Right. Okay. So this picture shows you the centrifugal compressors where we have the impeller. Right. This impeller is the rotating element. Right. And here is the diffuser where there is no rotating element. So the pressure is first built up in here. Right. So when the flow leaves the rotating element, it falls into the diffuser, in which you can see that the cross-section area of the diffuser increase. Right? So the velocity reduce and the kinetic energy due to the velocity reduce will convert into the pressure energy. Right? So we will have high pressure come out here. Right? So first pressure is built up here, and the second pressure is built up in the diffuser here. Okay, so this is called the centrifugal compressor. Right? Here show you both centrifugal compressor and the centrifugal turbine. Right? So sometimes they call it a radiant compressor and the radiant turbine. Right? Both are the same, right? Except one is expand, right? Which is a turbine. Another one is compressed, which is the compressor. Right? The characteristic of the flow, right, in the centrifugal compressor or the centrifugal turbine is that the flow will flow in the middle. Right? When the flow in, it flow in the center of the device or in the axial direction here. And when it leave, it's gonna leave in the radiant directions, right? In the radiant direction here. Okay. Compare with the axial flow compressor, which show below here. Right? The flow is in the axial directions and also leave out in the same directions, not in different direction like in centrifugal compressor. Right? The flow in the axial compressor will maintain its directions, right, along the axial directions until it leaves the axial compressors. Okay. This slide show you the compressor characteristic curve. Right? The compressor characteristic curve where we have the pressure ratio on the vertical axis, and we have an air mass flow rate on the horizontal axis. Okay, and inside we have different line here. The dark line here represent the speed of the compressor. Right? Represent the speed in terms of revolution per second here for the compressor. Right? And the dotted line, several dotted line here, give you the line of constant compressor efficiency, such as this dotted line represent the efficiency of the compressor at 0.55. Okay, so in overall, the compressor characteristic curve will give you 4 parameters. The first one is the pressure ratio. The second one is the air mass flow rate. The third one is the speed. And the last one is the efficiency of the compressors. Okay. How do we use this compressor characteristic curve? Right. We use this compressor characteristic curve in order to plot the way that we're going to operate the compressors. I show you 2 ways to operate the compressor. The first way is if we want to operate the compressor under constant pressures. That means no matter what flow that happen to the compressor, right, the pressure ratio of the compressor have to be kept constant. Right? So what we have to do, we just make this blue line here, draw this blue line here, so that we know that when the flow changes, right, when the air mass flow rate changes, what speed of the compressor that we need to drive in order to maintain the constant pressure ratio here, right? And if you run the compressor along this blue line here, which is the line of constant pressure ratio here, the efficiency of the compressor also change with the mass flow rate and also the speed, right? You can run the compressor from low efficiency to high efficiency of the compressor, right? And then if you increase the amount of flow, and that means you have to increase the speed of the compressor, then the efficiency of the compressor will go down. Okay, so first the efficiency of the compressor go up, and later on it's go down. How about the variable pressure ratio? Right? If you run your compressor, right, and change your pressure ratio along with the air mass flow rate change, right? Again, the speed of the compressor have to change also. Right? The speed of the compressor have to change also. Right? How about the efficiency? The efficiency will go from low to high, higher and higher, and then it will go low again. Right? It will go low again. Right? So as shown on this left curve here. Right? So this is the characteristic of the compressor when you run the compressor. Right? You can run either under constant pressure or under variable pressure ratios. Right? But when the mass flow rate changes, the speed of the compressor also changes, right? And the efficiency of the compressor changes as well. Okay. 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 Let's look at the calculations, right? When we perform supercharging or turbocharging, right? To do the calculation, we have to rely on the analysis of the thermodynamic cycles. Right? So I show you here 2 pictures. The first one is the PV diagram, the pressure and the volume diagram of the naturally aspirated engine or the engine without superchargers. The second one is the engine with the supercharger. We call it a supercharged engines. Right? Look at the first one here. Right? This is the common one that we used to see in our previous lectures. Right? We have both the positive work and also the negative work that come out. Right? The negative work is called the pumping loop work, right? Because we have to use the work in order to draw the air, right? Draw the air inside the engines and then exhaust it out. Okay, so we have to provide work in order to do the so-called scavenging process here. Scavenging or the gas exchange process here, right? This happened in the naturally aspirated engine. For the supercharged engine, right? You can see that we have no negative work. We have no negative works, right? And we do have the blow down work because we use the exhaust flow, right, to drive the turbine, right? So this is called a blow down work, right? So these portions that not happen in the naturally aspirated engine because we directly send the exhaust out to the ambient, right? But for this supercharged engine, this exhaust will flow to the turbine before it flow out to the ambient, right? And by doing this, the pumping work, right, instead of being a negative work, it becomes the positive work for us, right? The work that we need to use to draw the air now, we don't need to provide the work to draw the air, and we don't need to provide the work to push the exhaust out, okay? Because the exhaust will draw by the turbine here, okay? So this work become the positive work for us, right? So the total indicated power, or the total indicated work that we receive from the supercharged engine, right, will be what? Will be the area here, which is common to the naturally aspirated engine, plus this less color area here, right? So the indicated power is higher in the supercharger engine than in the naturally aspirated engine, and that's the reason why equipped with supercharger or turbocharger, right, the engine can deliver more work and can have higher efficiency. Okay. Okay. Now let's look at the analysis. Right. If we use the superchargers, right, we have only compressors. Right. The approach that we use to analyze the compressor is by using the first law for the steady state flow process, if you still remember, right? So we have a low pressure air flow in, and we also have a high pressure air flow out, right? So we have all property of the air that flow in, and we have all property of the air that flow out, such as the pressure, the specific volume, the temperature, and the internal energies. This E represents the internal energy, right? So we know that, right, by definition of the enthalpy, right, the internal energy plus the pressure times the specific volume is equal to the enthalpy. So by applying the first law for the steady state flow here, right, what we have is what? We have the rate of heat minus the rate of work is equal to the mass flow rate, which is constant. Mass in equal to mass out. Time with what? Time with the entropy that flow out plus the kinetic energy plus the potential energy, right, at the outlet conditions minus the enthalpy, the kinetic energy, and the potential energy at the inlet conditions. Right. So when you look at this term here, that inside the blanket, the big blanket here, right, it will be better if we can define another term that we call stagnation enthalpy. Right? The stagnation enthalpy, or sometimes they call it the total enthalpy. Right? we define by this H with subscript 0 here. Okay. This stagnation enthalpy is the amount of the enthalpy plus the kinetic energy per unit mass. Right? The kinetic energy per unit mass. Right? By defining the stagnation enthalpy, right? The first equation or the equation above here, right? If it happened to be the adiabatic process, right? The equation here can be reduced to just only this, right? If it is the adiabatic process, we have no rate of heat transfer, and we also have no change of the potential energies. Right? So the amount of work required by the superchargers will be equal to the mass flow rate through the supercharger time with the change of the stagnation enthalpy here. Okay. Now, if we go back and look at the property of the working fluid that flow to the superchargers, such as pressures, right? We can do the same as the enthalpy, right? By defining P02 and P01 to represent the stagnation pressures. Like we have stagnation enthalpy, we can also have stagnation pressure, right? And this P02 and P01 are the stagnation pressure at the outlet and the inlet of the superchargers, right? How we define? Same way, right? Stagnation pressure is equal to the static pressure plus what? 1/2 rho c square. This term is the velocity pressures, right? So the stagnation pressure or the total pressure is equal to the static pressure plus the velocity pressures, right? And we can also apply the relationship that happen in the isentropic process between the pressures and the temperature under stagnation conditions and under static conditions, right? According to these equations, right? P0 equal to P times with T0 over T to the power of gamma over gamma minus 1. Gamma represent the ratio of the specific heat or the letter K in thermodynamics, right? And this T0, right, is called the stagnation temperatures, where T0 is equal to the static temperature plus the velocity due to the flow, right, in terms of C squared over 2 times C sub P, right, the specific heat of that working fluid. Okay, so now we have stagnation enthalpy, we have stagnation pressure, we have stagnation temperatures. Right. Okay, how about the compressor isentropic efficiency? I think everybody should be familiar with this term, the compressor isentropic efficiency. Right. It is defined as what? T0 under isentropic conditions minus T01, which is the actual conditions, divided by what? T02, which is the actual compression, actual condition after being compressed in the superchargers, minus T01, which is the actual condition of the air before flow into the supercharger. Right? So when you look at these equations, right, it just come out from the definition of the compressor isentropic efficiency, which is what? Is equal to the isentropic work divided by the actual work. Right? The above one represent the isentropic work. Right? If the compressor work under isentropic conditions, the second one or the below one here represent the actual amount of work, right, for these superchargers. Okay, so look at this graph with plot between the enthalpy and the entropy. Right? Now, instead of having only two pressure lines, right, if we consider the kinetic term, which represent the velocity, right, into our considerations, right, instead of having two pressure lines, now we will have four pressure lines altogether. Right? P1 represent the ambient condition, which we consider is a static. Right? P01, right? P01 represent the pressure immediately in front of the compressor, right? Because immediately in front of the compressor now the air have a velocity. Okay, so we have a stagnation pressure 0, 1 here. And when it's compressed, right, when it's compressed, if we do not take into effect of the velocity, right, the compressed pressures will be P2 here. Right, is the pressure that we do not the effect of the velocity or the static pressure, right, P2 here. And if we include the effect of the velocity of the working fluid when it is being pressed by our device, right, that use the rotating element, right, then the outlet pressure that we consider also the kinetic energy, right, will be the stagnation pressure at the outlet with it P02, P02, right, okay. So P01 and P02 different from P1 and P2 because we include the term of kinetic energies, right, or the velocity in here, right. The line of the process, if we consider that it is the isentropic process, right, it still go like this in the vertical line, right, even between P1 and P01 and also P2 and P02. And that's the reason why when you go back to these equations, that's the reason why we can use the kinetic relationship, not the kinetic, the isentropic relationship, right, between the stagnation line and the static line, right, like this, right, because here is still a vertical line here, right. So we can have P01 equal to P1 times with T01 divided by T1 to the power of gamma over gamma minus 1. Okay. Okay. How about if we look at the overall from 01 to 02S, which is the isentropic process. 01 to 02S, if we apply the isentropic process relationship, this is what we have. T0 to S, right, equal to T01 times with P02 divided by P01 to the power of gamma minus 1 divided by gamma, right? And we can replace this T0 to S back into these equations, the isentropic efficiency of the compressor. And this is what we have, the isentropic efficiency of the compressor. So the actual amount of work on the compressor, right? Actual amount of work on the compressor can be found from these equations. Right? The actual amount of work on the compressor is what? M dot Cp times with the difference between T02 minus T01. Right? So so we use this isentropic efficiency equation to find the amount of T02 minus T01 because it's going to be equal to what? T02S minus T01 divided by the isentropic efficiency of the compressor. And that's how this equation come out, the actual work on the compressor. Remember, right? All the working fluid in here is air, right? In the supercharger, all the working fluid is just air. Okay, so this is how we can calculate the actual work that we need for the supercharger, right? Which is the amount of work that need to deliver by the engine. Okay, in terms of supercharger, the engine have to provide this much amount of work to the supercharger. Okay, how about the turbochargers? Right, for the turbocharger, the part of the compressor is the same, right? Okay, so in case of turbocharger, this amount of work now, instead of coming off from the engine, right, it have to come off from the turbine. Okay, so we have to do some calculations on the turbine. Okay, that's the reason why in terms of turbochargers, they only show you the turbine portions on the enthalpy and entropy diagram, right? The way they do the analysis is exactly the same, right? Turbine work under steady state flow process. So we have to apply the first law for the steady state flow process. Here we have 4 pressure line as well. Right? In your lecture, please draw this P3 line here as well. Right? We have 4 pressure line as well. Right? And we do the same as we have done on the compressor. Right? The actual work from the turbine will be what? The mass flow rate of the exhaust, because our turbine is run by the exhaust. So the actual work from the turbine is the mass from the exhaust. Time with what? The enthalpy change, right? From what? From stagnation enthalpy at point 0.03, right? To the stagnation enthalpy at point 0.4 here. Right? So this will be the actual amount of work, right? So the dotted line represent the actual process here, right? The full line here represent the isentropic process here, right? The efficiency of the turbine, right? The isentropic efficiency of the turbine is what? The actual change of the stagnation enthalpy divided by the stagnation enthalpy change if the process happen to be isentropic process here, right? Or in other words, it is the actual amount of work delivered from the turbine, we represent by S03 minus S04 divided by what? The isentropic work, right? We represent by H03 minus H04S. Okay. So using this isentropic efficiency and also the isentropic relationship between the pressure and the temperature, we can come up with these expressions for the isentropic efficiency of the turbine. Right? We can do this because we can have this relationship, which is the isentropic relationship between T04S and T0 flow, right? With the expansion pressure ratio that happen in the turbine here. Okay, so using this and the isentropic efficiency, we can come up with the new expression for the isentropic efficiency that show like this. And again, right, if we want to find the actual work from the turbine, right, which come out from the mass flow rate, or in other words, the exhaust mass flow rate, time with the enthalpy change, right? So in terms of isentropic efficiency, right, we can have the amount of actual work shown in these expressions here. Okay, remember on the turbine side, our working fluid is the exhaust gas, not the air. but on the compressor side, it is the air, right? So for superchargers, we have only one compressor, so we deal with only air. But for turbocharger, right, on the compressor side, we deal with the air, but on the turbine side, we deal with the exhaust gas. Okay, so that is the analysis of the supercharger and the turbocharger that we use the first law for the steady flow process to do the analysis. Okay, next, look at the examples. Look at the examples. Okay, we have a 4-stroke diesel engines that is to be designed to operate with the following characteristic at the sea level, where the ambient conditions, right, are what? 103 kilopascal and 10 degrees Celsius. The brake power that delivered by this engine is 260 kilowatt. Right. The specific fuel consumption is 0.244 kilogram per kilowatt hour, and the engine speed is 1500 RPM. The volumetric efficiency of this engine is 0.78, and the air-fuel ratio is 17 to 1. Okay. The first calculation that they want to do you to do the calculation is what? Calculate the required engine capacity and the anticipated mean effective pressure. So this is the first questions, right? For the engine, for this engine, right? Now this engine is equipped with superchargers, right? For ordinary engines, now they become a supercharged engine, right? So that this engine may be operated at an altitude of what? 2,700 meters higher than the sea level, right? At that level, the atmospheric pressure is 73 kilopascal, right? Another information that they give us when this engine equipped with supercharger is that the power taken by the supercharger is 8% of the total power produced by the engine. So now the engine have to deliver 8% of its power to drive this supercharger. And the temperature of the air leaving the supercharger is 32 degrees Celsius. The air-fuel ratio and the thermal efficiency remain the same. That means the air-fuel ratio is still 17 to 1. The thermal efficiency, they do not given, but they said remain the same. Right? So as the volumetric efficiency. Right? Then they ask you for the second calculation. Calculate the increase of the pressure at the supercharger to maintain the same net power output of the engine. So that means the supercharger have to compress the air to at what pressures, so that the engine still deliver what? 260 kilowatt, right? But the actual power that the engine have to be delivered is not 260 kilowatt, right? Because now it have to provide some of its power to run the supercharger, and that power amount of power is 8% of the total power output, right? So the total power output produced by the engine have to be higher than 260 kilowatt, right? With this higher amount of the total power output, right, then they can deliver its power to run the supercharger while keeping or delivering the same power output with it 260 kilowatt for use. Okay, take the gas constant for the air equal to 0.287 kilojoule per kilogram Kelvin. Okay, let's look at the solutions. Right, the first engine is considered to be the naturally aspirated engine. Okay, So we first calculate the fuel consumptions in order to determine the amount of air consumption, right? The fuel consumption can be determined from the specific fuel consumption times the brake power, right? And then the amount of air consumptions or air consumed, right? Since we know the amount of the fuel, we know the air fuel ratio 17 to 1, right? So one portion is equal to 1.057. If we have 17 portions, we represent the amount of the air. The amount of the air will be what? 17.97 kilogram per minute, right? And then we use the given information on the volumetric efficiency, which is 0.78, right? So by definition, it is the actual volume flow rate divided by the swept volume flow rate, right? Okay, the actual volume flow rate, our working with the air, right? So in order to find the actual volume flow rate here, right, we time it with the pressures. Underneath here, also the same pressure, right? So above here we have PV dot, below here we have PV dot S, right? The first one, PV dot here, we can consider our air to be an ideal gas, right? Because even though under the compressions, right, if it's not that very high, our air can still be assumed to be an ideal gas, right? So by that, this PV dot become M dot RT, right? We already know the amount of the air flow rate or air consumption, right? We know the gas constant for the air. We know the temperatures in the temperature of the air, right? Which is 10 degrees Celsius, right? So the first term done, right? How about the term below here, right? We know the atmospheric pressures of the air, 103 kilopascal. We don't know the swept volume, right? Never mind, just leave this swept volume here. We know the speed of the engine, and it is a two-stroke, right? It's a two-stroke here, right? So with this, we now can solve for the swept volume, right? From the volumetric efficiency, we can get the swept volume, right? And from the swept volume, we can get the brake mean effective pressure for this four-stroke engine, right? By knowing the brake power, by knowing the swept volume, which is L times A, right? And by knowing the speed of the engine, and because of its four-stroke here, so N here is equal to 2, right? So we can give the answer for the first questions. Now, our engine is equipped with superchargers. So we have a supercharged engine here, right? So the total power produced by the engine now have to be what? 260 kilowatt plus the power that it needs to deliver to the supercharger, which is 0.08 times 260. Right? So the overall power produced by the engine must be 280.8 kilowatt. Okay. 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 This expression that this calculation, right, that we come out, right, it come out on the concept that we assume that our supercharging is an ideal one, right? That means we have no loss in the shaft that connects from between the engine and our superchargers, right? So the mechanical efficiency is equal to 1, right? And our supercharger is directly connected to the engine. So all of the power taken by the supercharger is directly added to the engine powers. Right? So that are all our assumptions, right? Before we can come up with this total power produced by the engines. Okay. Now with the total power produced by the engine, we know the mass of the fuel required, right? Because we know the specific fuel consumption, we know the power output from the engines, right? And since we know the mass flow of the fuel, we can know the mass flow of the air. Okay, okay, know the mass flow of the air here. Okay, and we can now calculate the volume of the air induced at the superchargers, right, at the outlet conditions. At the outlet condition, inlet condition already know, right? Since we know the mass of the air is constant, so we can use this mass of the air to find out the volume of the air at the outlet condition, right? Again, we think of the air as the ideal gas. So the volume will be mRT at the outlet divided by the pressure at the outlet. The temperature at the outlet already given, right? So the volume at the outlet, right, we can calculate in terms of the outlet pressure P2 here. Right? So how to get P2 here? We go back and use our volumetric efficiency because it is the same. It is the same, right? The volumetric efficiency. Okay, so we know the volume of the air inducted, right, by the superchargers, which is 1699 divided by P2 here, right? And we know the swept volume, right? The swept volume of the engine, which is 0.0242, and then time with what? 750 will come out from 1500 divided by 2, right? So we can solve and get the outlet pressure P2, which is equal to 120 kPa. So the amount of the pressure increased by the supercharger will be what? From 73 kilopascal to 120 kilopascal, right? So the amount of the pressure increased by the supercharger is 47 kilopascal, and the pressure ratio of the supercharger will be what? The outlet pressure divided by the inlet pressure, which is 1.644. Okay, so that is example number 1. Okay. About another examples, right? We have a 6 cylinders, 4.8 liter, the size of the engine, supercharged engine operating at 3,500 RPM, right? And it has an overall volumetric efficiency of 158%, greater than 100, which is possible, right? Because we equip this engine with a superchargers, right? So the volumetric efficiency can go higher than 100. Okay. The supercharger has an isentropic efficiency of 92% and a mechanical efficiency in it linked with the engine, right, of 87%. 87%. So it's not an ideal supercharging. Right? The previous example, we think that this is the ideal one, so the mechanical efficiency is equal to 100. But now the mechanical efficiency is just 87%. The engine is designed that the air be delivered to the cylinders at 65 degrees Celsius. So the temperature of the air after being compressed by the supercharger have to limit itself to 65 degrees Celsius. And the pressure is 180 kPa. Right? So this is the condition of the air that flow into the cylinder. Right? The ambient condition is 23 degrees Celsius and 98 kPa. Calculate the amount of after cooling need. Remember, we have one configuration of supercharger or turbocharger that equipped with an intercooler. Right. So now they are, what is the amount of the after cooling needed in terms of kilowatt? Okay. The second question is the engine power loss to run the supercharger. Right. It's not, in fact, it should not consider loss because we intend to use some of the engine power to run the superchargers. Okay. So I put a remark here, right, to make clear about the aftercooler. Right? The aftercooler or the intercooler is needed because the compressed air temperature, right, that come out from the supercharger, you expect that it have to be higher than 65. Right? If it's not higher than 65, you don't need this aftercooler. Right? But since they ask for the aftercooling need, that means the air temperature that come out from the supercharger have to be greater than 65 degrees Celsius, obviously. Okay, so the solutions. Okay, so from the definition of the volumetric efficiency, we can calculate the amount of the air mass flow rate that is charged into the engine cylinder, right? That is what the volumetric efficiency times with the density of the air, the displacement volume of the engine, the speed of the engine divided by the number of crank revolutions, right? All terms here are given, right? So we have the mass flow rate of the air equal to this. Then we use the isentropic relationship, right? If our compressor run under isentropic condition, the outlet temperatures under that condition will be according to these expressions, right? We know T1, right? Because we know the ambient conditions, which is 23. We know the outlet pressure. We know the inlet pressure, right? It is the air, right? So the outlet temperature under isentropic condition will be what? 355 Kelvin or 79 degrees Celsius, which is already higher than 65. But this is under isentropic condition. How about the actual temperature? The actual outlet temperature, we can find out from the isentropic efficiency of the compressor, right? To find out what is the actual temperature T2 here, right? All term here, all the temperature here we know. So the actual temperature that come out is what? 84 degrees Celsius, higher than the isentropic one and higher than 65 degrees Celsius. So that's why we need the aftercooler, right? So the amount of the aftercooling need in order to reduce the air temperature back to 65 will be what? The cooling that this aftercooler have to perform will be equal to what? The amount of mass for the air times the specific heat of the air times the different temperature between what? The compressed air temperatures minus the inlet air temperature to the cylinder, which is what? 65 degrees Celsius, right? So the amount of aftercooler have to be 5 kilowatt, which is represent the capacity of the aftercooler unit. Right? The second question, the engine power need to drive the supercharger, right? Is the power to drive the supercharger in order to compress the air from ambient conditions to the outlet condition that we require, right? Which can represent by the change of the temperatures, right? We have the outlet temperature equal to what? The actual one, which is 357 Kelvin, right? And the inlet one, which is 23, right? So this is the actual temperature, right? Divided by what? The mechanical efficiency, right? Which is 0.87. So this will be the amount of power that the engine need to deliver to the supercharger, which is equal to 18.4 kilowatt. Okay, so that is it for our lecture today. By the way, I would like to go back to this one. Okay, the pulse turbocharging again. Okay, just to make sure that you understand. The first one is very simple because we would like to have a constant pressure. So that's why we make the exhaust manifold as big, as large as possible. right? In order to kill out the pressure pulse, right? But when we kill the pressure pulse, we also kill the kinetic energies, right? Because when the exhaust fall out from the cylinder here, right? It fall out in the small pipe and then fall into the large pipe. So the velocity reduced, right? The velocity of the exhaust reduced, right? So the kinetic energy of the exhaust die out, right? So sacrifice for a constant pressure here, right? This region will have a constant pressure before fall into the turbine, right? And the constant pressure represent the steady flow, right? All of these problems come out because our exhaust flow is considered to be an unsteady flow or the pulsating flow, not the steady flow, right? So the constant pressure concept is to do this, right? Make exhaust manifold large. But for the pulse turbocharging, right? Pulse turbocharging concept, we accept the pulse, but we just want to minimize the pulse, right? Not to affect our turbine much. The reason that we have to accept the pulse, because we want to keep this kinetic energy in our exhaust flow, right? To be alive. We don't want to kill or die out our kinetic energy or the exhaust kinetic energies, right? So we have to sacrifice our turbine by letting our turbine to receive the power flow, but we will try to minimize these pulsing effects to our turbine, right? By using two concepts. The first concept is to let the flow, the exhaust flow in sequence, right? To make the exhaust flow in sequence, right? We need two inlet pipe here, right? Two inlet pipe to our turbine here, right? And each pipe here will receive the exhaust flow from the cylinder, right? And it will alternately send this flow to the turbine, right? So the first pipe here connect to half of the cylinder here, and another pipe here also connect to half of the cylinder here, right? And in half of the cylinder, we still have two small pipe here, right? So every time that the exhaust flow happen, right, it never flow in the same pipe twice. This is the main concept, right? Never flow in the same pipe twice. So when this green pipe have the exhaust flow, the second exhaust flow will flow into either the blue or the red one, right? Because the first inlet pipe already have the exhaust flow. So the next flow of the exhaust flow have to go to the second pipe. So that means the second exhaust flow have to come out from either the blue or the red one, right? And the same concept apply to this or small flow pipe. If the green one already sent the exhaust flow, so the next flow will not come out from the yellow, from the green, not from the next one should not come out from the green. It have to come out from either three of these, right? Then if the yellow come, right, come out, if the exhaust flow come out from the yellow one, the next exhaust flow should come out from either blue and red. Okay, right. It never come out from the green because that means this inlet pipe will repeat the exhaust flow to the turbine, right? Which is prohibited, right? So in order to have a sequential exhaust flow, okay, so this is concept of the sequence. How about the minimum overlap here? The minimum overlap here, that means we want to have the sequential flow, but we do allow to have the overlap that happen in this sequential flow, but we try to minimize it, right? So the way we minimize it is that, right, if we have the exhaust flow, right, flow in the yellow line here, the next exhaust flow should not come in the yellow line. It should come in green, red, or blue line, right? Either one of these, according to the cycle that happen in the cylinders, right? So if the first exhaust come in the yellow, right, the next exhaust have to come in the green, red, or the blue, right? So sequence happen on this, right? And the minimum overlap can also happen because of this. Because the minimum overlap can happen because we have only one inlet pipe here. We have only one inlet pipe here, right? So that's why sometimes the overlap of the exhaust, that means the exhaust from the previous flow and the exhaust from the present flow, right? It may overlap with each other because we have only one inlet pipe here. Okay, so the sequence still the same. That means if exhaust come in from yellow, the next round should not come from yellow. It should come from either green, red, or blue. Okay, if it come from blue, if it come from green, then the next round should come from yellow, red, or blue. Okay, and but no matter what flow, what exhaust flow that come out from either one of these, there will be only one inlet pipe here. And by having only one inlet pipe, right, the overlap can happen, right? But we just try to minimize the overlap that happen, right, by using 4 pipe here. Okay, so just want to come back over and make clear that you understand all of this concept between the constant pressure turbocharging and the power turbocharging. Okay, so this is the end of these lectures. Okay, so bye bye.